Okay, so good afternoon, everybody. Thank you all for coming. Today we're going to try to speak. Uh, this so okay, now it's better. So today we're going to try to learn how the video codecs works under the hoods. But anyway, before I start, I want to tell you that I don't have a Twitter account or a Facebook, but I'm not also a runaway. I don't like this kind of stuff. But feel free to ask me any questions using the hashtag KA on the Twitter. Uh, before I want to start, I want to clarify some stuffs. For instance, this subject is very broad, and it's almost impossible for me to explain all the details that this subject has. And then I want you to be aware that I will skip lots and lots of details, and I will do lots of oversimplification of this complex matter. Our main goal is that you guys here left this room learning at least how encoder works on the overview, so you can kind of see how it works and why we need the compression at all, as one good question we need to answer, and what is actually what codec. But let's start with the simple question. Why do we need compression? This is like the first question we should ask before we understand what is a codec or a video compression. Anyway, so let's build our senses around what is a digital video, by working in a small scale. Let's say a pixel is the smallest concept we can have while dealing with images or video. And one can think, how can we code or encode a pixel into a computer? We could use a single bit, and therefore we could have two different colors, like black and white or red and blue, whatever. Or we can choose to encode our single pixel using 2 bits, which give us 4 different colors options. But let's go with 1 byte, which is 8 bits for sure, and that gives us 256 options. So, but a single bit, a single pixel is not so fun. We can't do much with a single pixel. So one thing we can do is group them together to make a picture, and that picture has a simple property that you all know, that width and height, which describe precisely what is a picture. It's a bunch of grouped pixels. Okay, but how much does it cost? We start putting like costs on 1 pixels, and then with that idea, we can go further and see that if we multiply the height by width, by the bits per pixel we're going to spend, we have like 16 bytes that we would need to encode this simple image. Okay, but again, colorless images are not so fun. So let's add image, or let's add color to this this thing. One of the things people, we as a human being, we are good to see. We are, let's say, in a very simplified way, we are perceiving colors mostly using the 3 primary colors: red, green, and blue. And that the idea is to form colors using red, green, and blue is not new, but it's the way we're going to add color to our simple before picture. When I was a child, I tried to mix things like red and blue and green and paint, and it always kind of finished with a brownish color. It doesn't make any color at all. So that kind of thought about how mixing red, green, and blue, it's not the right thing to think about. A more appropriate way to think about colors is when you think about, like, you can have a spinning wheel where you can put the 3 primary colors, and then you spin it very fast so you can see the color formation. On the screen you can see like some kind of pink. But anyway, another fast experiment you can do is like put source of light, red, green, and blue, and then block these lights, and then you see color formation. You can see like there is pink, there is some kind of orange and yellow. But anyway, the idea is that using RGB or red, green, and blue, we can form colors. And that's nice. Now we are on the third dimension. We can think of that because that idea that we have for a single image, now we multiply that by 3, and then we have a colored image. Okay, so what's the cost of the color? So since we add 3 more bytes to encode the color, we can multiply the resolution by 3, and then we have 48 bytes. That's the cost of this single picture here, this small picture. Before we move on, I want to clarify another stuff here. That is, when I talk about this small block, I want you to think about that this small block is just a small picture of, it's just a simplified block from the huge or greater image. And another thing is, when you see colors or you see planes, I want you to think about them as a matrix of numbers, not as a colors, because in the end the colors will, or the numbers will be converted to colors. Cool. So, but again, a colored picture is good, but without motion it's not a video. So one thing we can do is go to the 4th dimension, which is time, and then what we can do is like take one picture after the other one, like in a frequency by, let's say, 30 frames per second, and we can have this illusion that there is movement. So this is like the basic idea of a movie, and that's pretty basic. I hope you all understand that. And this also has a cost. For instance, 1 second it's responsible for by 1,300 bytes, which is a lot. Now that we have this knowledge, let's try to see why do we need compression at all. Let's take a single TV episode with 1080p, 30 minutes long. It would require us to have 250 gigabytes to storage that kind of file, and that's a lot, and that's not even feasible. Although you have a huge HD, but it's not like something that we can deal with. And another problem is that if you think in terms of bandwidth, we would need to have 1.11 gigabits per second, which is not so easy. And I think you as a Brazilian people know that bandwidth is not so good down here, but anyway. And with that all in mind, I ask you what we can do now that we know that it's impossible to watch some, it's impossible to have this bandwidth to watch 1080p movies, but anyway, we still continue doing that using Netflix or other service. And what we can do is basically 3 things. One of them is explore how our vision system works, how our eyes perceive the images or the world, to reduce the correlations in time, or space, sorry, and reduce the correlations in time. Space and time is the following. When I'm talking here to you, my head is moving, my mouth is moving, but the background is mostly static. And this is like, even in time, this is also true for the many times. So we can exploit these properties. Let's start with the simpler one, which is exploiting how our vision system works. So basically, and again, it's a very oversimplification, light comes into our eyes, and then we have like millions of photoreceptors on our eyes that converts that light to impulse, that's something that our brain can understand. And it turns out that these photoreceptors are divided mostly by 2 types, which are cones and rods. Being the cones mostly responsible for fine details and colors, and the rods are the one responsible for like brightness, black and white, darken, this kind of stuff. And our eyes have 120 millions of rod cells and only about 6 millions of cone cells, which make us better to see light and darkness than colors. And that is easy to understand when we have this small experiment. So many of you are looking to this chess figure here, and then we can see that there's two small blocks, A and B, if I'm not wrong. And I guess for many of you, these blocks seems to be colored in using different color, but in reality they are not. If we connect them with the line, we can see that they are the same color. It's our brain playing tricks to us in order for us to see better the luminosity or the brightness than the color. So the point here is we are better to see luminosity than color. With that in mind, some of the guys thought, well, how can we encode color and like in a way that we can separate the luminosity information from the color? And they came up with an alternative model to red, green, and blue, which is YCBCR. This model, it produces the same final result of red, green, and blue, but it can kind of separates the luminosity from the color information. And why is that good? Because since we know that we are better to see light luminosity, we can discard color information. Okay, so here are some formula that you guys can. You are pretty smart that you can understand that how you can convert from RCBCR to RGB and from RGB to ICBCR. But anyway, the idea is that one I told you. I want to separate the luminosity information from the color information. This color information is like the chroma blue and the chroma red information. And there's one technique called chroma subsampling, which is just this idea that I can, instead of using the full resolution to the chroma or the color information, sorry, I reduce the resolutions, therefore I can save space. So, and it's easy for me to format it again. I will lose information because I will lose information about the color, but the final picture is the same. So just to have an idea, I don't know if it's clear for you, but the image above is using like the full data, the full RGB, quote unquote, to form an image, and the above one, or the below one, is not using. It's using half of the data needed. And you can see that they are pretty much the same for most of us. And when they are in movement, it's very, very easy to see any difference at all. And this technique, using only this technique, we go from 250 to only 125, which is a great saving. But anyway, now we have another thing we can do, which is correlations in time. What is this? So let's say that we are encoding a video that are, and there's lots of different videos, but they do have this almost the same concerns and issues. But let's focus on these videos. A ball is moving through the static background, and therefore you and I, being human that are intelligent, think, why do we need to again encode the information about the background again and again and again? So the basic idea about the reduce information on time is just this. So you have the one frame, and then another frame you just want to encode the difference. So how this is done? One of the simple techniques is the frame difference, which is you take the frame 2 and subtract to the frame 1, and then you have the difference, and you can kind of encode and send only that information to the storage or through the network. And let's say I apply that technique. Instead of sending all the information, I send only this small block here. Again, this is a very oversimplified thing. There's lots of complications, but this is enough for you to understand. And what is the cost of this kind of technique? We need to encode that we are referencing a previous frame, and then the difference on the current frame also needs to be encoded. But if I tell you that there's another way that we can do that better, well, there's more smart guys on the world that we can think of, and some of them thought, what if instead of we making the difference, we try to describe the movement, like the ball is moving. Let's try to describe its movement instead of only encoding the difference. And it turns out that you can do that. I'm not going to go to the further details here, but now we can make what we call a better prediction, because we can kind of predict that the ball is moving from x, y something to x, y something. And this technique turns out to be more saving beats than the other one. So when we compare the two techniques, one can see that the motion estimation technique, which is the one that I told you about, the prediction or trying to describe the movement, it requires less bits to be centered. There is this command here that you can run on the FFmpeg, and let me see if I can try to. Oh, gee, no, I could not. Sorry, here. So you can run this command on FFmpeg, and then you can kind of see, as I told you, this information about the direction of something moving. It's hard to see because it's mostly static here, but let me, here. You can see that there's movement in here. That is this kind of prediction. The algorithm is trying to predict that the back of the back of the rabbit is moving from that part to that part. Anyway, let me go back here. Okay, so that technique is very good. It's very good. But can we do that through all the frames? No, we can't, because the first one is pretty obvious. We can't do that because we don't have a previous frames to reference from. The other ones it's okay, but as you might notice, when you are watching a move don't always go from like they often go from one scene to another scene, and this change scene, they are not very profitable in terms of bit saving when you think about encoding the difference between time. So this technique can be applied always. So it's not so good. What kind of techniques we can apply? So there is correlation also in space, which is the next technique we're going to discuss with you. When you take a picture of something, no matter what is it, you're going to see that there's a lot of similarities in that picture. There's a lot of places that they have if not the same color, they have the same patterns. And it turns out that these patterns, you tend to follow a direction, even like the left, or right, or down, or upward, anyway. And this, we can exploit that, because if you see that there's a direction going further in a picture, in a very, very long path, we can kind of encode that in a way that it's not so costly for byte, in terms of bytes for a codec. So what we can do is, suppose we're trying to, this is a static, this is like we're not using the prediction over time here. We're trying to predict what is the values of those blocks in here. We kind of know them, but we want to do the small amount of bits possible to send to the codec. One thing we can do is look at the neighbor colors and see that there's a trend. Let's say in this case, I see that there's a trend of 100 going down. There's 100 again, and 200. And then I make a bet. I make a prediction that this is going to do the same. We're going to continue it throughout the pixels. So this is my prediction. But then, in reality, that's not always true. I not always make the right precision. So I take my prediction and subtract by the real data from the frame, and then this gives me what I call residual difference, which is a much better metric that I can compress. It's more easy to compress something that there's no much of information. Okay, so what is the cost of this kind of technique? We need to encode the direction. We also need to encode this difference, which is the difference, the prediction that we did about the space, subtracted by the real thing. Okay, so here's are some predictions. They are used by the HG64 But anyway, this is just for you to see that even if you look pretty closely on an image, you can see that these patterns repeat over and over and over. So this is one kind of technique. Cool. Now that we know this, all the stuff we discussed it here, I'm going to try to do with you. We're going to try to implement a codec here so it's easier for you to understand. I'm going to call it Piper. So let's start with the boring, not boring, but the more precise concept about what is a codec. A codec is a device or a computer program for encoding or decoding a digital data stream or signal. Think about the codec is the junction of an encoder plus the encoder parts, or the decoder parts, sorry. So you have a, sorry. So you have source, a source for video source, which can be a camera. Jeez. 1 minute. What can be a camera, which is creating, sorry, creating pictures, and then we send these pictures to the codec, to the encoder, and then this encoder will try to compress the data, and then this compressed data that is the thing that we transmit through the internet, or we store it. And then we have the other part called the decoder, which will take this compressed file and try to make it to look like the original one. That's the basic idea. And here we're going to try to focus on the encoder part, not one, because we don't have enough time to explain that, and the other because the other part's like the inverse situation. Almost all the codec works in a similar way. These blocks describes parts of how a codec works. Although we have different codecs from like commercial codecs, open source codecs, they almost always work in the same way. They have these building blocks. The first one is the picture partitioning, which is we take a picture, like let's say 1080p, and we're not going to work on the 1080p picture. We're going to break down this picture in smaller block, which are like 8 by 8, 16 by 16, 14 by 14. Anyway, why this needed? This is needed because we need to, we can kind of make the prediction about how something is moving. Like for instance, the head of the guy is moving. It's easier for us to make a prediction about the movement of the contour than the background. The background is mostly static, as I already told you. The other step is the prediction that we already talked about. Okay. And the another step after we did the prediction are the transform. Let's start by trying to establish what is a transform. A transform is like thinking of a function that receives x and double it. Anyway, it's something that takes x and makes y. That's the idea. So there is one transformation which is able to transform data from like pixel to the one of the, how can I say, one of the representation that we are able to see what is most important about the picture, what is not most important, sorry. So the idea is we have a function that we apply to the pixels, and then we can have a result as another array resulted from that, which will show us the smaller part here. Let's say the upper part is the most important and the lower part is the less important. And how is that done is very complex, but let's say that each value of that new array is like a sum weighted average of the whole block. But anyway, let's make an walkthrough, which will make the process more simple. So this is a block of memory, and we can see that we can have like the numbers, the pixels and numbers on the side. We decide to use not a RGB but a single one to make it easier for us to understand. And then we can take this matrix and apply a transformation. This transformation can be any one, but the one we are using here is called DCT. Uh, and then this transformation will give us another array, which is a different array as with the same property as I told you. And the question is, why do we transform something into something else? Why is this really necessary? So I told you about the properties that the lower triangle of this newer array is where the data can be dropped. So here is where we can say, oh, for this bit rate I want, or for this video I don't mind to lose data at all. So I can describe or discard data. So one thing we can do is we can, for instance, we can drop the 50% of this array, making all zeros, and then we still have something that is very similar to the another one. And this is only using this technique I told you. There's no more techniques. And here it shows it is very blocky because we are given a very zoom on the picture. But in a real life, so you see it in a small, bigger screen, and then you see 1080p. It's harder for you to see. But another example can be this guy here. So you have the left one, which is the 100% original, and then we have the right one, which is using only 15% of the data required on the first one. So I think using only this technique, you can see that we can save a lot of data, and that's impressive. Okay, so let's say not the final step, but one of the final steps are how we can encode all this information I told you in a manner that a decoder or your smartphone or television will be able to play that video. So we start with a small block, and then we make some transformation, projection, then we make some transformation, and let's say we end up with this array here, this matrix here. So one thing we can do is we need to transform this 2D data to 1D. What we can do is to zigzag scan this matrix using a special form that will give us let's say the right way where is the 0 are. So when we do the zigzag, we're going to have this new instead of having the information in like on a matrix, we're going to have this in line. And what we can do with that, so we can kind of see the probabilities of the symbols. Now as we're applying like the normal compression that you guys probably already know, which is we take some symbols, let's say in this case 27, 10, and 0, and then we qualify them by how many of them are used, like taking the probability. For instance, for the 27, we have 1 out of 16, the probability that of that symbol occurs within that table that we have. With that in mind, we can kind of create a bit code. It's like we are creating a table that instead of using a whole byte, we can use bit code, which is smaller, but we need to have this information. For instance, so 0 is the most occurring pattern on the previous matrix that I showed you. So we're going to assign it to a smallest possible bit code, which is 0. And then we have the 10, which is the second one. We're going to encode it using the bit code, like 10. It's like what? It's not 10, it's 2 in binary. But anyway, you got the idea. And then we have like this idea of once we have the bit code, what we can do is replace the original numbers by the bit codes. For instance, we have 27, 10, and 10. So instead of spending a whole byte for that thing, we can spend 3 bits, 2 bits, and 2 bits. So the idea is we go from 16 bits to only 3 bits plus the table. We need to have the table to construct back the symbol. Oh, sorry, the array, the matrix. There are a lot of other techniques applied to this step, but like run left encode and any other techniques. But I mean, the idea is to take most of the information we have and make it less and less and less in any possible way. Just to give a heads up, so they have this concept, which is if we have a background that is not changed by the other picture, the previous picture. So we can spend a single bit to skip the whole thing with no information. We can say skip this block because it's the same from the previous frame. And that's the idea. It's compressed the most possible way. And that's the only way we can achieve like 4K or 60 frames per second, and this thing we want to have in the modern days. Okay, the idea, I think you guys got the ideas. It's not so hard to grasp. Once you have, again, it has a lot of details, but the main idea is not so hard to understand, I guess. But we didn't talk about how a decoder works. So the decoder, let's think about as a reverse step on the whole thing we did. So instead of entropy coding that is making the zip, we unzip, that's quote unquote unzip, and then we, instead of quantize or throwing away bits, we're going to put them again, and instead of making a transformation, we can apply the inverse transformation. It's like a function that you have an inverse function, and then we, instead of doing the prediction, we're going to apply the prediction we did. So since we know that we need to move something to here, we can apply that. And and now we can think that if we think about how we start this whole thing, we start with the two. We started with the 250 gigabytes, and then we went down to the 1.125 gigabits, applying the chroma subsampling, which is getting the information about the color versus the luminosity. And then applying all those techniques I just showed you, we go down through 1.32 gigabytes, which is amazing. So now we have this idea that we can watch a full HD movie or full HD with a bandwidth on only 6 megabits per second, which is, I think, is pretty amazing. Given that the amount that we need originally, with no compression at all, go down to this much, is for me is almost as a miracle. But anyway, now that I finished, I can kind of walk through and answer the simple question: how newer codec can be better than the other ones? For instance, here we have the same video, one spending 4 megabits per second, and the other one spending 2 megabits per second, but using different codecs, one older and another one modern. And we have another situation here that apply almost the same thing. And it turns out that what we can do, what the people does is they trade off processing power by, they insert complexity. And for instance, now our computers and our smartphone are more capable of doing processing. Then we change, we kind of make an effort, we make a trade-off. We throw away, we're going to spend more time while on CPU, but we're going to be able to do more bigger resolution or more quality videos. That's the basic idea. So we talk about the blocks and everything, like the predictions. So if we compare, this is again an oversimplification. If we compare 8264 with the HAVC, we can see that there's more and more from the 8264, we have 16 direction from prediction, while on the HAVC we have 32 predictions, which is make this more and more accurate. And also it has a bigger blocks, so it has more advanced, it also uses the parallelism that we have in a smartphone and other techniques. But the idea is that we will change processing power by this concept of getting more resolution and more quality under our screen. So that's it. I think so. This is this talk is very summarized from a broader subject. I wrote about this in this link in here. If you are interested, you can access it. You can access it. And also, I was asked to give you guys this small thing here. I don't know what have in here, but it's not a PS4. And I'll give you, if you have any question, you can kind of make them through me, or use it like the Twitter. I can see here there's no one question, but anyway. And if no one has any question, the first one will be here. We'll get this small baggage. Okay? Thank you. Okay. So if you have any question, you can talk with me, and that's okay. Thank you.